All right, welcome to this online lecture that covers stoichiometry. So before we begin about stoichiometry, let's take a look about climate change. It's hot, and the reason why is that there's too much carbon dioxide. So we know that the average global temperatures depend on the balance between incoming sunlight and outgoing heat lost to space. And so we can see that in the picture over here. So sunlight comes in and it warms up the earth, and usually, when the sun goes away, we get some heat lost to space. Now greenhouse gases are a good thing, but too many greenhouse gases are not a good thing. So greenhouse gases allow the sunlight to warm the earth, but don't allow it to escape in order to cool it. So we do want some, otherwise all of the heat will be lost to space, and we would heat up and cool down too quickly for life to even be able to survive. But, however, too many greenhouse gases and we get a constant trapping of heat. And that's what's happening with our CO2 levels. So carbon dioxide levels have been rising and leading to climate change, which is basically an increase in Earth's average temperatures. Since 1860, the carbon dioxide levels have increased about 25%, and the temperature, average Earth's temperature, has risen 0.7 degrees Celsius, which doesn't seem like a lot, but I guess it is significant. So the primary cause of rising carbon dioxide levels is burning of fossil fuels. All right, that's where we get most of the energy that we use, to heat our houses with, and for automobiles and stuff like that. We usually get it from burning fossil fuels. So here's an example of an equation. This is octane. This is an example of fossil fuel that's burnt in our cars as gasoline. So we can take a look at this equation and see that for every 2 moles of octane, we produce 16 moles of carbon dioxide. Okay, remember those coefficients are going to tell us molecules or moles. Okay, they don't tell us mass, but they tell us either, for every 2 molecules of octane, we get 16 molecules of CO2. Or if we look at it on a more macro, bigger scale, 2 moles of octane is going to give us 16 moles of carbon dioxide. Okay, so knowing the world's fossil fuel consumption, we can actually estimate the world's annual carbon dioxide production, okay, which I guess they've done calculations, and it matches the measured annual atmospheric CO2. So we know that the increase in carbon dioxide levels since 1860 has been directly related to the burning of fossil fuels. And so how do they do that? Well, the calculation is basically a form of stoichiometry. Stoichiometry is relationships between chemical quantities in a balanced chemical equation. So it allows us to predict amounts of products that will form in a chemical reaction based on the amounts of reactants we have, or if we know how much product we're forming, we can figure out how much reactant we'll need. Okay, either way, it's a relationship between products and reactants. And so the concepts of stoichiometry are very similar to a cooking recipe. So if we see here this very simple recipe to make pancakes, 1 cup of flour plus 2 eggs plus a half a teaspoon of baking powder is going to yield or react to form 5 pancakes. Those look delicious, by the way. All right, so let's take a look and see how this works. According to our recipe, if we have 2 eggs and enough of everything else, we can make 5 pancakes. So the relationship in our recipe is 2 eggs makes 5 pancakes. Well, what if we have 8 eggs? Okay, well, if we have 8 eggs and enough of everything else, then we can make 20 pancakes. And we know that because we have this relationship here that 2 eggs equals 5 pancakes. So we can use that as a conversion factor. In fact, that's what we see here. If we have 8 eggs instead, we can get rid of eggs and turn them into pancakes by using this conversion factor. With 5 pancakes is going to take 2 eggs. So if we do this, We 8 times 5 is 40 divided by 2. We can get 20 pancakes if we have 8 eggs. This is the same kind of thinking for stoichiometry in chemical reactions. A balanced chemical equation is basically a recipe for how reactants combine to form products. So here's a recipe to make ammonia, NH3. Okay, we can take 3 molecules or moles of hydrogen gas, and we could take 1 mole or molecule of nitrogen gas, and we're going to get 2 molecules of ammonium in the end. Okay, just like taking 1 cup of flour plus 2 eggs plus a half a teaspoon of baking powder is going to give you 5 pancakes at the end. This is our recipe for this chemical reaction. And remember, the coefficients can tell us either molecules, okay, or on a much grander scale, it also is the same thing as moles. So if we have 3 moles of N2 gas and more than enough H2, how much ammonia can we make? Well, here, okay, just like when we were trying to figure out how many pancakes we can make with 8 eggs, okay, we're going to start out with moles of N2, and we need to figure out moles of NH3. So we can use the conversion factor that we get from our reaction, okay. 2 moles of NH3, okay, is going to be coming from 1 mole of N2. So what do? We always start with what we're given, 3 moles of N2, and in order to get rid of moles of N2 and convert it to moles of NH3, all right, we put the moles of N2 on the bottom. We use our conversion factor here that we get from our recipe, okay, to see that we can make 6 moles of NH3 in the end if we have 3 moles of N2. Okay, so this is basic stoichiometry. All right, so let's take a look at another example. Sodium chloride, NaCl, forms by this reaction between sodium and chlorine. And there we have it there. How many moles of sodium chloride result from the complete reaction of 3.4 moles of Cl2? Okay, assuming that there's more than enough sodium. All right, so just like our pancake recipe, our original recipe says if you have 2 moles of sodium and 1 mole of chlorine gas, you can make 2 moles of sodium chloride. Well, what if we have more than just 1 mole of chlorine gas? What if we have 3.4 moles of chlorine gas? How much sodium chloride can we make? Well, let's take a look. We start out with 3.4 moles of Cl2. Okay. And in order to get rid of moles of Cl2, we put them down here on the bottom. And we have to figure out how many moles of NaCl. All right, so our recipe up top says that 2 moles of NaCl, okay, are made when we have 1 mole of Cl2. So if we do the math, 3.4 times 2 is 6.8. Okay, so our answer is 6.8 moles of NaCl. All right, so if we start out instead of with just 1 mole of Cl2, if we have 3.4 moles of Cl2, we can actually make 6.8 moles of sodium chloride. All right, so here is a question for you to try. So take a minute and stop this after I'm done explaining, and go ahead and try and see if you can come up with the answer that you see down on the bottom of the screen. It says water forms when hydrogen gas reacts with oxygen gas according to the balanced equation. How many moles of water result from the complete reaction of 24.6 moles of oxygen, assuming that there's enough hydrogen gas? All right, so you guys can pause it and do the work and make sure that you get the correct answer. Okay, so thus far we've been going from moles of reactants to moles of products, or moles of products to moles of reactants. Either way, we've been talking about moles. However, in chemistry, remember, we don't have a scale that measures moles. We have scales that measure mass. And so mass is what we're going to be physically working with in the lab. So what we need to do is we need to add an extra few steps to going from mass of one reactant in the chemical equation to mass of another. So if we need to find the mass of the product from the mass of the reactant, okay, first we need to, the mass that we start with, okay, mass A, all right, and then we convert that to moles, and then we can use our ratio from our recipe, right, to go from moles of A to moles of C, okay, and then we can convert using molar mass on our periodic table back to mass of the product. Okay, so if we have A plus B is going to react to make C, and we know the mass of A, and we need to figure out how much mass of C is actually going to be made. We go mass of A. We use the molar mass of A to change it to moles, and then we use the mole ratio that we have from our recipe to change it to moles of C, and then we use our molar mass to go back to mass of product C. So let's take a look at an example. It says calculate the mass of CO2 emitted upon the combustion of 500 grams of pure octane. Okay, so we saw this equation before when we were talking about global warming, but now we're going to actually do something with it. All right, so we always start kind of, by figuring out what we have and what we need to get. So in this particular question, it asks us to calculate the mass of CO2. So we need to try to figure out how many grams of CO2 is being made if we have 500, the dot, okay, which means those zeros are significant. All right, so that's 500 grams of octane. So how much carbon dioxide will we get if we burn 500 grams of gas? All right, well, we start with what we're given, 500 grams, okay, of C8H18. Okay. Now, first thing we need to do is convert it to moles of C8H18. All right, and we got to get rid of those grams. So we're going to put grams on the bottom. All right, once we get rid of those grams, okay, now we've got moles of octane, but we need to actually get to mass of carbon dioxide in the end, so we need to convert that, we need to switch that over to moles of CO2. So we're going to get rid of our moles of octane by putting it down on the bottom, and moles of carbon dioxide on the top. Okay, so that'll cancel out those moles. And then finally, we need to go grams of CO2. And so we will get rid of moles by putting it down there on the bottom. Okay, so now that we've set up all of our units, let's plug in some numbers. So if we take a look at our periodic table and we add up the mass of 8 carbons and 18 hydrogens, okay, that's going to be our molar mass. So 1 mole of octane is 114.26 grams. Okay. Now, for the next step, we have moles of CO2 and moles of octane. So that's where we look at our periodic table, our recipe, our chemical reaction. That's a relationship between the products and reactants in our chemical reaction. So according to the coefficients, we have 16 for carbon dioxide, and we have 2 for octane. All right, and then last but not least, we look back at our periodic table for the mass of carbon dioxide. So in 1 mole of carbon dioxide, we have 44, okay, 0.01 grams of carbon dioxide. Okay, so if we do the math, if we multiply everything on top and we multiply everything on the bottom, then we divide the two, what we're going to get is 228.52 grams of CO2. Okay, but we got to round that to only 3 sig figs because that's how many sig figs we started with. So our answer will actually be just 229 grams of CO2. Okay, so if we have 500 grams of octane, we will be making 229 grams of carbon dioxide. Let's do one more example together. In photosynthesis, plants convert carbon dioxide and water into glucose, C6H12O6, according to this reaction below, which hopefully you recognize from biology. It says, how many grams of glucose can be synthesized from 58.5 grams of CO2? Well, let's start with what we're given. 58.5 grams of CO2. Okay, and first we need to get rid of grams, go to of CO2 and go to moles of CO2. Okay. Once we cancel those gram units, okay, we can go from moles of CO2 to moles of glucose. C6H12O6. Okay. And then those will cancel out the moles of CO2. And we got to go to, it says grams of glucose. All right, so we're going to use our molar mass to do that. Okay, and that will cancel our moles. So let's plug in some numbers. So 1 mole of CO2, we look at the periodic table, and it's going to be 44.01 grams. Okay. From our recipe, up here, we've got, let's see, 1 mole of glucose is made from 6 moles of carbon dioxide. And then if we add up C6H12O6 on our periodic table, we'll get 180.18. Okay. Is 1 mole of, that's how many grams are in 1 mole of glucose. So if we do the math, multiply everything on the top, divide it by the numbers on the bottom, we will get 39.9 grams of C6H12O6 or glucose. So we start out with 58.5 grams of CO2. We will end up with 39.9 grams of actual glucose. All right, so this is the last little slide for our review of stoichiometry. This is a you try it, so you're going to pause and answer this question. One component of acid rain is nitric acid, which forms when NO2, a pollutant, reacts with oxygen and rainwater according to the following equation. Assuming that there's more than enough oxygen and water, how much nitric acid in kilograms forms from 1,500 kilograms of nitrogen dioxide pollutant? And please, when you do this, don't forget to convert grams to kilograms first, because remember, in molar mass, it's moles per gram, not moles per kilogram. So convert 1,500 kilograms to grams first, and then do it, and then convert back to kilograms after. All right, good luck, and if you have any questions, please let me know next class.